This is Fundamental Problem 6 from Chapter 19. The reel has a weight of 150 pounds and a radius of gyration about its center of gravity of 1.25 feet. It's subjected to a torque of 25 and starts from rest when the torque is applied. We want to find the angular velocity after 3 seconds. The coefficient of kinetic friction between the reel and the horizontal plane is 0.15. Okay, so in this problem, we could use this equation here for impulse momentum for linear momentum and equation 1912. But instead, we're going to use an equation which is similar to equation 1913. Remember, for some of the other equations that we had on the equation sheet, we said, like here for equation 18.7, this was for the instantaneous center of zero velocity. But you could use the same equation with the moment of inertia about 0.0 instead. So we're going to use something like equation 1913, but we're going to do it about the instantaneous center of zero velocity. So we have the moment of inertia about the instantaneous center times the initial angular velocity plus the sum of the moments about the instantaneous center integrated with respect to time from t1 to t2 is equal to the moment of inertia about the instantaneous center times the final angular velocity. Okay, so we're starting from rest. So the initial angular momentum is equal to 0, and the sum of the moments about the instantaneous center is, well, we need to draw a free body diagram first. Okay, so, Okay, so here, the reason that we're going to use the instantaneous center is it's easy to find the location of the instantaneous center. That's right here where the rope is coming off of the wheel. And in this case, they're giving us a coefficient of kinetic friction because this point is actually going to be moving relative to the ground. So this is not rolling without slipping. But when you have the rope coming off the wheel, this point is the instantaneous center. So that's kind of like if it was rolling without slipping, this point comes down and then it leaves. And when it's right here, it's not slipping relative to the surface. But when the rope is coming off the wheel, this point is the instantaneous center of zero velocity. Okay, so if this point is the instantaneous center, as the wheel's rolling this way, this point would be moving this way, which means friction's acting the other way. So we have a coefficient of kinetic friction. We have a force of kinetic friction, which is going this way. We have a force of gravity, which is acting straight downwards. We have our torque, which is going this way. And we have the tension in the rope, and that force is pointing to the left. Okay, now we have to see how many of these forces are actually going to appear when we sum up the moments about the instantaneous center. Well, the torque doesn't because that's acting right, or the tension doesn't because that's acting right at the instantaneous center. The force of gravity doesn't cause rotation, so this and this don't appear. The torque does, that's in the positive direction, that's 25. And the force of kinetic friction, that would cause rotation this way. So let's say we're summing it up with this being the positive direction. So the 25 is positive, and then we have minus force of kinetic friction times that distance from here to here is 1.5. That could all come outside the integral because everything there is constant. So when we integrate, we would just get delta t, which is 3. This is equal to the moment of inertia about the instantaneous center times omega. Okay, I know the moment of inertia about the mass center because they give me the radius of gyration here. So this is the mass. The mass is 150 divided by 32.2 times k squared, that's 1.25 squared. Then using the parallel axis theorem, the moment of inertia about the instantaneous center is this. For the parallel axis theorem, it's moment of inertia about the mass center plus the mass times the distance squared. So plus the mass of 150 divided by 32.2 times the distance between the old axis and the new axis. The old axis was right at the center. The new axis, that would be this inner radius is 1 foot. So this is plus 1 squared. So for my moment of inertia about the instantaneous center, this is 150 divided by 32.2 times 1.25 squared plus 1 squared, which is just 1, times the angular velocity. Okay, so to finish then, all I need to do is find the force of kinetic friction. Now, you can just look at this and you can say, the normal force wasn't on here. I do have a normal force, but it doesn't cause rotation. So it wouldn't appear when I sum up the moments about the instantaneous center of zero velocity. But if you want to apply this equation here in the y direction, you don't have any velocity in the y direction, so using the impulse momentum relationship in the y direction would tell you that the normal force is equal to m times g. And we know the force of kinetic friction is equal to the coefficient of kinetic friction times the normal force. So this is the coefficient of kinetic friction times m times g. The coefficient of kinetic friction is 0.15 and m times g is 150. Okay, so let's put that in here and we get 25 minus 0.15 times 150 times 1.5. It's a lot of 1s and 5s, times 3 is equal to 150 divided by 32.2 times 1.25 squared plus 1. 1.25 squared plus 1 is 2.56 times the angular velocity. Okay, and that's easy to solve. You should get 3.459 radians per second for the angular velocity.